Okay, my name is Dustin Casper. I'm a third-year medical student from VCOM-Auburn. This current project we were working on was determining the relationship between MYH7, which is found to be upregulated in heart failure patients, and something we've now tagged as MYH7 antisense and the relationship that carries. So as we all know, heart failure is one of the #1 contributing costs in healthcare, and it's an average of $43 billion a year that is spent on that. And so previous research done by my professor, Dr. Pandorf, found a relationship in rat models that through an upregulation of MYH7, which was found to be upregulated in heart failure patients, you would have a downregulation in this MYH7 antisense. And this relationship was found to be connected through something that was called miR-208B, which is just a sequence of RNA found in rats, which was manipulated through that MYH7 antisense. So this created the hypothesis, okay, that maybe if we could control this and regulate this long non-coding sequence antisense, we could regulate miR-208B and then ultimately try to decrease the MYH7 that's upregulated in heart failure patients. So he proved this in Figure 5. You can see that in rats that were put under hypertensive conditions and they ultimately developed concentric hypertrophy, it resulted in an upregulation of MYH7. Now, if you were to take that away and you were to look at it just in the sense of a normal, non-hypertensive heart, just like you and I, then we ultimately get a decrease in that MYH7 regulation and an increase in the MYH7 antisense. So that's where we came in and we started looking at it. Okay, we've done it in rats. So now let's try to find this in humans. So we went on to RNA Central's websites and we found these long non-coding RNA sequences that could potentially work for us in humans, and we landed on 2 of them. Figure 4 shows the 2 potential candidate sequences we used, which were ending in 6-9 and 7-1. These sequences, once we did that, we could create primers which are dedicated to target certain sequences within there and create the products that we wanted. Those products would then, we confirm them through reverse transcription, PCR, and electrophoresis, and then we could send them out for sequencing. Figures 6 and 7, they show us, creating products that were creating ideal products through the long non-coding RNA sequence ending in 6-9. We proved it, and then we showed its relationship with miR-208B, which is ideally what we're going to be regulating through this antisense sequence. Once we did that, our goal was to kind of find the bounds of that long non-coding RNA sequence. And in order to do that, we looked for things that we could identify either on the 5' or 3' end. Figure 8 shows where we were able to identify an exon located on the 5' end, and we created a primer that directly targeted that, and then ultimately allowed us to look at that, find the end sequence, and then we could prove that through our electrophoresis, and then it allowed us to find that final piece. And lastly, on the 3' end, we were able to use a specific primer, oligo-DT, which allowed us to target that very end poly A tail attached to it, and then we could sequence all the way through to that. And so now that we've got these exons located and we've gotten them sequenced, within that sequence is our desired MYH7 antisense. And by targeting the antisense, our goal is to be able to look at that and then regulate it and control it and manipulate it, because that will directly result in a change in the amount of MYH7. And if we can regulate that, then we can reduce the effects of heart failure. We can potentially reduce the concentric hypertrophy, which puts pressure on hearts and results in people, being stuck in the hospital for months at a time and costing, billions of dollars to everyone. So that's the ultimate goal. The next step for us is to look at it and to actually get the entire sequence. We've got one end and we've gotten the other end. We just need to connect the dots. And once we do that, we can fine tune and directly manipulate that long non-coding MYH7 antisense, and then ultimately be able to create a therapeutic agent that could help ideally reduce the effect of heart failure on patients. So yeah, so that's all that in a nutshell. So.